That's Konstantin Hicke. He did his studies at the Technical University in Berlin, and in particular did his diploma thesis on dynamics and synchronization of delay-coupled semiconductor layers. In this context, we've already been collaborating in the recent past, and he's going to present some of the results of that work that he did with Hicke at the Technical University in December today. If you're interested also to discuss it further with Konstantin, he'll be here until tomorrow. So feel free to address him, and we're looking forward to your presentation.
Thank you, Ingo. Yeah, welcome everybody. Thank you for listening to my talk. The topic is dynamics and synchronization of two delay-coupled lasers, especially in the case with delay mismatch. The talk is structured as followed. First, I will introduce the problem by using a generic model, not especially applied to photonics or to coupled lasers. Then I will move on to the Lang-Kobayashi type systems. This is a standard rate equation model for simulating semiconductor lasers. I will present the solutions for external cavity modes. These are standard solutions for semiconductor lasers subject to optical feedback. And then I will present phase space dynamics of the coupled lasers and the mode hopping. The mode hopping phenomena. As Ingo told you, this is the content is part of my thesis, my diploma thesis, but it's also kind of work in progress. So at some points I have some open questions, some results, but not the answers yet. As you will see. First, we begin with a generic model. We have two coupled systems. These are the differential equations for the time evolutions of these two systems. These can be lasers, for example, but also for example coupled neurons or so on. This equation depicts the case where we have the coupling between the two systems is conducted via a relay in the center between the two coupled systems. This you can see by these two terms, namely because the first system is getting feedback from the second systems with the coupling strengths K. In the same manner, the second system is getting feedback from first system with the same coupling strength. And the systems also get feedback from themselves. That's why here's X1 and here's X2. Here you see the time delay between the information propagation from one system to the other, or from the system to the relay and back to the system itself, and that is that shows that the relay is absolutely centered in the middle between the two coupled systems. In the case of the lasers, we have often the case of a passive relay. That's, for example, a semi-transparent mirror. So some output of the laser is reflected and reflected back to the same system, or it is transmitted through to the other system. And the coupling strength for the coupling between the two different systems, I denote cross feedback strength, and the feedback strength to the system itself, I call self feedback strength. And it was found out that the introduction of this relay in the center between the two coupled systems leads to the case that the two systems synchronize, even if they have chaotic output. The new point in the model I've been investigating is that the relay between the two coupled systems is not exactly centered, but is off by by delay mismatch denoted delta tau, so that, for example, in this case, system 1 gets feedback with a delay time of tau plus delta tau, and the second system gets self-feedback with a delay time of tau minus delta tau. This you can see here. The overall feedback, the cross feedback, is as in the case before, has the delay time tau. What we now expect is that the system, both two systems, don't synchronize isochronously, as in the case where the relay was in the center, but we expect a time lag between the time series of the two systems, and the time lag has the value of delta tau. So we haven't, in that case, the isochronous synchronization, but general, in this case, kind of lag synchronization.
So the x1 and x2 are scalars?
No, these are, in this case, for lasers, these are vectors of the intensity and the carrier density. But it can also be different parts. For example, for the neurons, you have the
action potential.
Right, the potentials. To prove that this general lag synchronization indeed exists, what we did do was to introduce a symmetric and an anti-symmetric variable, namely this S of t denotes the synchronization manifold, and this A from t is transversal or orthogonal to this manifold. And here you see it's some kind of median between the two expected synchronous signals, namely signal 2 at time t and signal 1 at time t plus tau 1. If you do a calculation of the time evolution of these two variables, then we can expect that we have a synchronized solution, a stable synchronized solution for A equals 0, because the part orthogonal or transverse to the synchronization manifold is 0, and if A dot is 0, then this synchronous state or symmetric state is stable. So we do a linear stability analysis of these two equations. I just, for brevity, I printed the one for A only, and namely around A equals 0 on the synchronization manifold. So we see the time evolution of the antisymmetric variable depends on the system Jacobian times A, and this term L minus K. These are the two coupling strength, and these are lots of delay terms, which kind of which kind of work against the synchronous state. These are the abbreviations. And if we now have a symmetric coupling, meaning that the coupling strength between cross and the self feedback is equal, then these delay terms vanish, and the time evolution of A is only dependent on this term. And so we can say that all eigenvalues, instantaneous eigenvalues, I have to tell you, of the system have negative real parts, then the synchronized solution can be considered stable. We will move on to the laser model.
May I have a question?
Yeah.
What happens if instead of asking that you have the coupling, the difference or the couplings, the self-feedback and cross-feedback being identical, you assume that the sum of both is 1, which would be the case for a semi-transparent mirror. That the transmitter plus the reflection is 1. That is the condition for a semi-transparent mirror in optics.
Yeah, but
what would happen with the analysis? It certainly does not vanish there. In that case, L minus K will not be 0.
Would not be 0. Yeah, then all these.
The sum wouldn't be 1, but a constant.
Would be 1 and a constant. Yeah.
It's a constant on 1.
Yeah.
Yeah, but then all these terms would
will contribute
to the asymmetric variable, and thus the synchronous state wouldn't be stable.
Because as far as I remember, numerically, they are stable. If I'm not wrong, at least in the case of the lasers with a semi-transparent mirror, you don't need to fix both strength equal to each other, but the total or the sum of both equal to 1, and then, if I'm not wrong, it is stable. So somehow that term should not contribute. But
we'll see.
Okay. But in numerical it is stable. Okay, go ahead. Go ahead and we'll see later.
We move on to the laser model. As I told you before, it's depicted by the Lang-Kobayashi rate equations. These are equations for the electric field and the carrier density N. This is the dimensionless form, so there are no units. And yeah. This alpha factor is normal form. It's the gain function, and yeah, coupled to the electric field itself. Now we add the term for the self feedback by the coupling strength K11, the coupling of laser output of laser 1 to itself. That's 1,1. And here's the inclusion of the delay mismatch. You see, for laser 1 it's Tor plus delta Tor, and for laser 2 it's Tor minus delta Tor. And we add the cross feedback, coupling between the coupling of laser 2 into laser 1, and vice versa. And the delay time is, as in the generic case, just Tor.
But you were assuming that the dynamics was the same for both.
I'm sorry?
You were assuming the dynamics before identity of the systems. No, it is not. You have alpha 1 and G1 and G2.
Not what I think, but representative. The generic case as representation for number.
You go back. You have the same sign. Yeah, F, that's 1 and the same function.
Only that you now allow for different parameters of the lasers, alpha and G. We can now be different while here was completely symmetric.
That's true. I included
This solution does not exist anymore.
That's right. But in the course of my simulations, most of the time the parameters were symmetrical, so this case actually applies. But I wanted to include this for
generality.
For generality.
Just pointing out that this lack synchronization solution is not or doesn't need to be a solution for the system. You might not, you cannot look for stability of the state which is not a solution. system equations.
But I think they will again be chosen symmetrically.
Actually, I investigated the effects of non-symmetric parameters on the synchronization probabilities, but I did that in numerical, just to make it not everything.
So can you repeat what the n variable is?
Sorry, of course. The n variable is the carrier density for the laser.
And does not couple back into the...
No, you have the coupling between n and e only in this direction. But that's not true. In the gain function, you have actually the n. It will show you the complete set of the equation you will see.
But then that's not the same than what you had before.
I'm sorry?
Then you cannot write that equation. You cannot write in the generic way that you were using a couple of slides before.
Yeah, because the k and n might be a matrix that apply only for one variable and not for the
Yeah,
other.
but that was okay.
But these x variables are actually state vectors, and they included are the field amplitudes and the carrier densities. So, and of course, for the laser system, you have to add some noise to account for the spontaneous emission. And another new thing I included into my model was that the gain function is itself not linear as in many simulations, but nonlinear with this mu factor that couples again the electric field amplitude with n. If you put mu to 0, then you have just a linear gain function in n. Yeah, and the white noise for the white noise for the spontaneous emission is Gaussian and no correlation in time or space. The other variables in the equations are timescales. The timescale parameter that's just for the transformation from actual physical system to the dimensionless system. The alpha factor is the alpha factor, the bandwidth enhancement factor. P is the pump current, and mu is, as I said, the gain saturation coefficient. Numerical simulations that I did of this physical system, of these coupled Kobayashi equations, reveal that indeed we have a perfect synchronization with the time lag in the amount of delta tau. The green and the magenta curve are the outputs, the intensity outputs. That's squared absolute of the field, of the electric field variable. And we see the tau, the delay time tau is 1000 and delta tau is 100. And if you look at these axes, and you will see easily that the time lag is pretty. Yeah.
So each laser alone.
I'm sorry?
What does each laser alone do? Do they oscillate only, or do they have chaotic trajectories? If they are uncoupled, what do they do?
They have chaotic output, but if you couple them together, they have two, but synchronized, so that both exhibit the same output, even if it's curved. And that's.
But a solitary laser would be stable, without feedback and without coupling.
Yeah,
that's what he's asking.
Yeah, without feedback. Yeah. We have to have the feedback for the encoding output. I have to mention that in this simulation, I disregarded the noise for the spontaneous emission, so we can see clearly these, not the similarity, but the equality of these two output curves. Another method of comparing two time series of a time series is by using the cross correlation function that kind of clusters the two outputs against each other, and at the shift with the greatest correlation, greatest similarity, we have the highest peak. In this case, it's the same parameter set as before, and you see in the inset here that here's the main peak, and neighbor to it are sub peaks, and these have a shift by tau from the main peak. But if we had no delay mismatch, then the two layers would be asynchronously synchronized. So the main peak would be at shift equals 0, but now it is at delta tau, and that's the 100 in this case. And that's another way to confirm.
In the previous case, you were talking about the perfect synchronization. I would like to know if here there is a reason for which we don't have the perfect synchronization.
Yeah. That's one simple reason. In this simulation, I included the noise, as I did not in the case before. That's right. I forgot that right. Yeah, that's right. If there was no noise, then this peak would actually go up to 1, exactly. So, what I investigated next was if the quality of the synchronization between the two time series of the laser output had any dependence on the delay mismatch itself. We have to consider that for this plot, the delay mismatch for the synchronization was included, so that the correlation coefficient which this figure depicts is always calculated between the one curve and the other curve shifted by delta tau, so that the synchronized curves lie over each other. And we see that for the case of delay time tau, it's almost makes no difference, or doesn't make any difference how large the delay mismatch is. Actually, I simulated until delta tau equals 900. That would mean that the one laser would get self-feedback with a delay time of 100 and the other one of 1900. And still the correlation coefficient, and that would mean the synchronization quality is almost the same. You notice that this curve is quite noisy, but that actually is reason in the simulation method that I used. I should have probably do more simulations and then do
average.
Thank you very much.
What happened at these isolated points where it fails?
Yeah, that's one question I couldn't answer yet. This one here, in my opinion, is the value directly after delta tau equals 0, and so maybe it's some kind of delta tau value in the phase range. But this I can not explain yet. It has the value I already.
Is that 333?
That's exactly. That's
one third of the tau, because at 500 you also have a big fluctuation. So it might be related to a multiple. And if you exactly catch that in the discretization that you take, if exactly the half or not, and maybe for
that's right, but I would expect that in this case, with exactly a third of the with data Tor exactly a third of the daytime, there would be no dip but a peak. I think this dip is directly behind the peak. This peak maybe, and here we have this one, but it's you see it's quite a few simulated points. I think there's only one pixel here, but actually I have found this phenomenon too for the calculation of the correlation coefficient with not shifted time curves, time series, so that we have a low correlation all the time, but not for the case of rational.
Something
ratio.
For the rational ratios between the one delay time, which includes Tor and minus delta Tor, and the other Tor and plus delta Tor. Yeah, but since the step size is the same all the time, if this were one anomaly, or not anomaly, but a single value dip, then we would see, this dip in the same size here as well, at 500, and probably at 750.
You never observe anti-correlation.
I'm sorry?
Always positive correlation, never anti-correlation?
That's right. For this case, yeah. If when I considered the correlation coefficient for the unshifted time series, then I got the case of anti-correlation. That's right. But this dip, I checked. I didn't just cut it off. It doesn't go beyond 0, but stays in the positive range. That's right. One would expect anti-correlation just directly behind the high correlation peak. Wouldn't one?
We can discuss that later.
So, another phenomenon just very recently found. I wonder why it didn't pop out during my work with my thesis, is that when in the simulation, the operating regime of the two lasers is the low frequency fluctuations regime, which is characterized by these peaks and those corresponding dips in the electric field, then if we exclude the noise, then the synchronization is again perfect. As you can see here, this is some kind of masked intensity difference between the two time series, and it's 0 all the time, here and here. This is the case for the included effect of gain saturation of the nonlinear gain function, and this is with the linear gain. Doesn't make much difference. But if we have the case of the coherence collapse regime, which has a higher pump current, for example, then for the case with the included gain saturation, we too have the perfect synchronization, but for the disregarded gain saturation, so the linear gain function, the two time series don't match, they don't synchronize, as you see here. Ingo told me that probably is the cause is just the specific parameter set, but I tried several parameter ranges, but this effect persisted.
If you increase the coupling also persists, or I think if you increase
the coupling, you mean? I don't think I increased the coupling, but I changed the pump current and the gain saturation.
Yeah, but then it's, if you increase gain saturation, you make it less chaotic, so you will synchronize. If you increase the pump current,
yeah, but
much, it's also more chaotic. You have somehow to force the synchronization, so you can force it by increasing the coupling and see what happens. Maybe this is
right, yeah. Yeah, I have to do that in this. Now we go over to the external cavity modes. External cavity modes are solutions for one Lang-Kobayashi type laser, and they are characterized by this ansatz, namely that the electric field is just a constant amplitude and the phase change with a constant frequency and a constant carrier density. And this is an analytical solution for a laser, for one laser subject to a single feedback. Now that we have this delay mismatch, we can simulate this problem by one effective laser, namely that we add the two rate equation systems so that we have one effective laser subject to two different feedbacks. One with a delay time tau plus tau, delta tau, and the other one with a delay time tau minus delta tau. And this is what we get. The analytical solutions for the frequency, the carrier density, and the amplitude for these fixed external cavity modes, which I would read ECMs. And here we see we have to evaluate the equation. We have to evaluate the equation for the frequency omega because it's a transcendental one. So we will do this numerically and then put these solutions for omega into the equation for the carrier density and the amplitude. But there's one more thing to notice, namely that the inclusion of the gain saturation or gain saturation coefficient mu here changes the solution for the carrier density. Normally it would just be minus 2 kappa and this term, but the inclusion of the gain saturation includes the pump current into the equation for the carrier density. We have to do some further evaluating work, and so that of course the amplitude has to be real, so the square amplitude must be greater than 0, and this leads to this condition for the carrier density, and this helps us to consider the only relevant, physical relevant external cavity modes, to which we will come now. This is a representation of the numerical solution of graphical solution for the transcendental equation for the frequency omega. It's just a linear function omega with just one. I'm so sorry. Steigung. Slope. Yeah, slope 1. And this function, and the intersecting points will be the solutions for the frequency omega. And we see here that this function is simulates an overlay between two two sinusoidal functions with increasing frequency difference, and this leads to this form, and that's why the ECM solution, which normally lie on an ellipse in the phase space of frequency and carrier density, will get in a different form as I'm showing now. Yeah. This is the omega n plane, with the plane frequency and carrier density. This is the ellipse I told you about. This range here is the range where the physical irrelevant solutions lie, so they've been cut off. Those red and green dots you see are the calculated modes and anti-modes. The green dots are the transversally stable eigenmodes of the system, and the red ones are the unstable anti-modes. This is for the case without delay mismatch, and now if we increase it according to this graphical or numerical solution, we have the formation of sub-ellipses inside the area of the former solution ellipse for the ECMs. For small delta tors, we have some kind of mode islands, but they get interconnected as we increase the delay mismatch. But the distribution of modes changes radically from the quite regular one in the case without delay mismatch to the case of a increasing delay mismatch. This slide I just depict the effects of the different laser resistance parameter on the position of the ECMs of the sound cavity modes in the frequency carrier density plane, the gain saturation. This here is the pump current, as I told you before. The coupling between the pump current and the gain saturation is only there if we haven't got a vanishing gain saturation, and because of this term, a higher pump current mean a higher general position of the solution ellipse in the phase space. But if we neglect the gain saturation, then we have just the same position for the ellipse, but the stable eigenmodes just decrease, the number of stable eigenmodes decrease until only one is left. The increasing of the coupling strength blows up the size of the ellipse. This can be understood from this, because kappa is just in the analytical sense the amplitude, and the higher the amplitude, the more intersection points you have for the numerical evaluation. So the larger the range for the ellipse gets.
May I ask a question there? The diagram of the alpha parameter, which is certainly the main non-inherited parameter, it looks like as if it had no influence on the synchronization stability. Is that what you also, let's say, find numerically? Does that agree? So alpha doesn't affect the synchronization?
No. Honestly, not. For in the range of very small alpha factors, there are lots of verifications, I think, and these affect the synchronization. Probably, This is just for a small range of alpha factors beyond the range of massive bifurcation scenarios that are just stacked up together. So, what I've now done is to project the dynamics of this simulated one effective laser, or the laser is subject to two self-feedbacks, or you might say the two synchronized lasers, onto this omega n on this frequency carrier density plane. The frequency is, okay, we can't really read this. It's Vs minus Vs of t minus Vs of t minus tau by tau. So it's a kind of phase change over the
One round trip.
round trip time. Thank you. So this is actually this projection on this plane means since this is the dynamics on the synchronization manifold, that this is only the case if we already have the synchronized case. And what I wanted to show you with this slide is that what great difference in the dynamics in the omega n plane it makes if we have delay mismatch or if we don't. This is the normal case where the relay is centered in the exact center, so delta tau equals 0. So so the dynamics just tend towards the downside of the ellipse, where the ellipse with a minimal gain is located, and if the dynamics come too close to an unstable anti-mode, the red ones, then there's an excursion, and the dynamics start again near the mode nearest to omega equals 0. That's the mode with the minimal line widths. And this is the case for the regime of low frequency fluctuations, which is characterized by in this case by a low pump current. This is the exact same parameter set, but with an included delay mismatch of 100. So the position of the modes and anti-modes is changed radically, and so is the dynamics in this phase space. You can see that more easily in these two diagrams. This is these are mainly the two axes. This frequency and this carrier density. And here you have more or less regular steps down this ellipse from one stable eigenmode to the next until the conflict with an anti-mode occurs, and then we have the excursion and start back here again. So the dynamics is fairly regular, and this is the case with the delay mismatch, and the excursions happen not just at the bottom of the ellipse, but can happen almost all the time, because the modes and anti-modes are much nearer to each other, and so the excursion can easily happen. And that's why this dynamic is so much more irregular. One other thing is the dwell time of the dynamic loops on these modes or anti-modes. This is a two-dimensional histogram, and the more colorful it gets, the higher is the dwell time of the complete dynamics at this point. So we can see that in the last case it was a large delay mismatch, where the modes and anti-modes are distributed not in that orderly fashion as it was with a small delay mismatch. Then we have irregular dynamic through the space with one center here, but it looks obviously much different in this picture. This is the former kind, the one with with no delay mismatch, where we have regular itinerancy through this phase space with not really distinct center of dwelling. Of course, this is the region where most of the time the dynamics excurse back to the minimal line width mode, but you see it looks fairly irregular. So this the effect of which I told you before. If we have a very small delay mismatch, then those mode islands form themselves, and the special thing is that the dynamics. I have to tell you that these modes form more or less independent of the size of the delay mismatch and the delay time itself, but the delay mismatch must be very small in comparison to the delay time. And so the dynamics of the system stays in the first mode island and is not able to leave it or to excurse or to tend back or forward to this island. This is after t equals 50,000, and this is after t equals 500,000. And can you see this? This is actually a 2D histogram of this case, and you can see the dynamics come to rest in one specific mode. In this first island, in this first mode island. So the fine-tuning of the delay mismatch in respect to the delay time can obviously lead to a single mode stable emission, and not just with some trick with high pump current and high gain saturation. This is again the regular case for the parameter set of these two of this case, and this is what the dynamics would look like if we have no delay time. It's as well the case of low frequency fluctuations, and you see the regular distribution of dwelling until here at the reachable end of the ellipse is the dwell center where the excursions back to omega equals 0 happen. So you see there's lots of open problems still. Here are some of them. And namely, I thought the distribution of modes and anti-modes in the omega n plane, what effect on the chaos dimensionality of the laser output could this have? I did lots of this work together with Valentin Klunkert from Technical University Berlin, and he is at the moment engaged in calculating the global Lyapunov exponents to look at the chaos dimensionality of the case with delay mismatch. Then what we spoke of before was the case of the non-symmetric coupling. I actually did some calculations, some numerical simulations with non-symmetrical coupling, so the self-feedback strengths and the cross-field self-feedback strengths differ from each other, and I can even show you the results later. But I would like to get more of an analytical sense what happens there. If you remember the generic equations where we first came to this case, then it appears to me that there are some analytical solutions left, which one can find out. And another thing is that's not in an analytical sense, but in a numerical sense or experimental sense. What happens, or how does a mismatch in the laser parameters, so different pump currents, different gain saturations, or different alpha factors, for example, how does this affect the quality of synchronization between the two lasers? And also I would like to evaluate the things related to the gain saturation. I showed you in these slides, they have a basis in reality. It should be not hard to show the laser dynamics if the modes increase to a higher carrier density, if we include the gain saturation, or if they do not. And what else is that my simulations show that the inclusion of the gain saturations slows down the itinerancy through phase space in this case. So the higher the gain saturations, the slower the movement down towards this ellipse. I would like that to be confirmed as well. Yeah, and of course, one of the big problems is that with all these simulations, the phases, coupling phases, which were included in the model, were not considered in all these simulations. I set all phases to equal 0. But through a collaboration with the paper that I'm preparing, what he is engaged to find out more about the effect of the phases and the synchronization properties of these phase including systems. So, and I think that's it. Yeah, it's just a summary. Thank you.
Thank you very much. Other questions? Comments? Maybe I can start with one. Looks to me there's quite an interesting aspect in what you show with the delay mismatch. Because you show that with the delay mismatch, this ellipse breaks up into these individual bubbles. Mm-hmm. That is something which is known from if you have a system instead of having feedback from a mirror, having feedback from a Fabry-Perot interferometer. Yeah. Which actually is also the case. You have two different delay times. You may say those are the two reflectors of a Fabry-Perot cavity, right?
But you have, in your case, what the case you mentioned is that there's the single mode, solitary laser mode in the middle, and then those bubbles shaping up from this point, right?
No, it looks very similar. So my question would be: so would you say that the synchronized dynamics, that if it synchronizes, would be the dynamics of a frequency filter feedback? Maybe we can have a look at that later. Are there further questions? So there were many during the talk, so let's thank Konstantin again. And we'll be around until tomorrow afternoon.
What we have, the people that they had to come. I don't